Hello, welcome to Blockish Dev. I'm Aishat Akinyemi. This video is a quick guide to scaffolding, testing, and deploying your first smart contract on the Cudos blockchain using the Cudos Blast CLI tool. In the last video, we looked at setting up our development environment, and in this video, we are going to use the Cudos Blast tool to create a smart contract project. We're going to have a look at the file structure and what a smart contract on Cudos looks like. At the end of this video, you should be able to create your own Cudos Blast. You should be able to scaffold your own Cudos Blast project and also create a simple project using what you learn from this tutorial. First things first, let's initialize the Blast project. So now I'm going to make a directory named Cudos Smart Contract, Cudos SC. From there, I'm going to now cd into Cudos Smart Contract and run Blast init. Make sure you're using the current version of Node that works with your system. Running Blast init Scaffold. So I'm now going to open the project in VS Code. We have a contracts folder that has two different contracts, the alpha and beta contracts. And then we also have the scripts folder. In the scripts folder, we have two scripts. We can deploy smart contracts and we can also interact with the smart contracts using the deploy and the interact.js scripts. I'm now deleting the beta contract directory. We have the state file. The contract state is defined by creating accessors to the state objects, which would be used to access the values on the blockchain using the unique key. Here on line 13, we have a constant constructor of type item, taking the struct state as its type. Each accessor to the values on the blockchain must have a unique key. In this case, we have it as state in small letters. Then we have the message.rs file. The message.rs file contains the definition of the messages that are sent to and handled by the smart contract. It may also contain the type definition of the responses sent by the smart contract, as you can see on line 25. It is important to note that each message, apart from the instantiate message, the execute message, as well as the query message, are enums whose variants are handled by the execute and query functions or entry points, respectively. Now, let's go to the contract.rs file. The contract.rs file has different functions known as entry points. When interacting with the smart contract, the different messages and queries are handled by these functions. You can think of a smart contract entry point as the main function of a normal Rust program. But they are different in that we have three types of entry points: the instantiate function, the execute function, and the query function. The instantiate function instantiates or initializes the state of the smart contract after deployment. Meanwhile, the execute entry point is used to perform an action that makes changes to the state of the smart contract. So whenever you want to write functions that handle changes to the state of the smart contract, you put that inside of the execute entry point. And the query entry point handles messages and interactions that deal with reading the state of the smart contract. When we want to define functions that handle the reading of smart contract state, we put it in the query entry point. So what parameters do the entry points take? The first one is the depth dependencies. It It allows us to read and update the smart contract state. The mutable depth allows us to update the smart contract state, while the depth itself allows us to read from the smart contract state, as well as querying other smart contracts. It contains methods that allow us to perform actions like verifying custom WASM addresses and some other actions. We also have the environment. The environment contains the blockchain state data when executing the message. Data such as the chain height, the current timestamp, as well as the called contract address. Thirdly, we have the message info. The message info contains the metadata about the transaction, such as the message sender and the amount of tokens attached to the transaction. And then we have the message that triggers the smart contract execution. We define the messages that we want our smart contracts to handle in the message.rs file. Now let's take a look at the instantiate function. The instantiate function takes dependencies, environment, info, and message of type instantiate message. In the instantiate function, we're going to initialize the state. We call the .save method of the state, passing into it the storage from the dependencies as well as the data we want to save. And it returns a result that's either a response or a contract error. Now let's look at the execute entry point. So it handles the messages of type execute message, and the variant of the type execute message would be one of the two variants defined in the message.rs file, either the increment or the reset variant. It uses pattern matching to decide which function should be executed. You would see that both variants defined in the message.rs file under the enum execute message are handled by the pattern matching. So if the variant is increment, then it calls the try increment function, passing it the depths. What happens here is that the update function, an update function, what happens here is that an update function is called on the storage item, passing into it a borrow to the storage object, and then a closure which would be executed on that underlying object. It's going to return a result that could either be a successful response or an error if the update fails. We can define custom error messages in our error.rs file. The second variant of the enum is the reset. When we pass in the reset variant, what happens is that it calls on the try reset function. And the parameters sent to that is the depths, the mutable dependencies, the message info, as well as the count. The message info contains the identity of the call as well as the payment, which is how much native tokens are attached to the call. In the update closure, we check if the info.sender equals to the owner of the smart contract. If it doesn't equal to the owner of the smart contract, we return an unauthorized error, which is defined in the error.rs file. And if it's the owner, then we're going to update the count. And on line 55, we update the count to the new count passed in the call. So now let's have a look at the query entry point. You'd see that the query entry point takes the dependencies, environment, and message of type query message. What is worthy of note is that the dependency here is not the mutable dependencies, it's of type dependencies. This is because we wouldn't need to mutate or change anything from the state of the smart contract. We only need to read from the state of the smart contract. So we're using pattern matching to decide which function to be called when a variant of the query message is passed. The only variant we have here is getCount, which doesn't take any it doesn't have any properties. So let's have a look at the query count function. The query count function returns a standard result of type count response. The count response is defined in our message.rs file. We read the value of the data stored on state using the load method of the accessor, which is state in this case. So state.load. So we pass in the read-only storage object, and when we get the state, we return its count. So this is a very simple function. Now let's go back to line 64. On line 64, we are calling the toBinary method on the results from query count. What this does is that it encodes whatever data type that is returned in the function call into a standard base64 binary data. Now let's look at the Rust tests. We have mock dependencies with balance, mock environment, and mock info. These are going to be used in our unit testing. So the first test is to see if proper initialization happens. We're going to create a mock mutable dependencies, and on line 83, we created a message of type instantiate message, and the count is set as 17. We also create a mock info called info on line 84, and we created its sender as creator, assigning coins 100 of denom earth. On line 87, we call on the instantiate function and passing into it the dependencies, the mock environment, the info, and the message. Then we call .unwrap to assert that this was a success, because this unwraps the value returned in the response object. So we assert that 0 equals the response message.length. If this passes, then the initialization was successful. Otherwise, it failed. And on 991, we'll call on the query. We're now going to query the state to see if it has set the initial state, the initial count as 17 that was passed in on line 87. And we also unwrap on line 92 and assert if 17 equals to the value .count. The second test in the test suite is increment. We create the info as we did in the first test. On line 104, we create another mock info, the sender being anyone. On line 106, we define the execute message as execute message of variant increment. And on line 107, we call on the execute function, passing in its parameters and unwrapping the results. So after the incrementing has happened, on line 110, we make a query call to the smart contract to get the current count. And on line 112, we assert if the value equals to 18 to ensure that it has incremented. Then the third test in our test suite is reset. Here we test if the reset works as we want and if the controls are put in place the way we want. The first thing to do is that on line 124, we test with an unauthorized info If you check line 120, you would see that when instantiating the smart contract, we did so with the sender as creator. That means if everything works as we want, only the creator should be able to change the smart contract count. And to check if this control is in place, on line 124, we try executing with execute message of variant reset. We are expecting an unauthorized error. If the contract error is of type unauthorized, then it does nothing. Otherwise, it panics and says must return unauthorized error. Down on line 132, we try resetting the count using the mock info of the creator. The original creator should be able to reset the count. When we pass in the auth info defined on line 133 with the sender as creator, the same sender that initialized or instantiated the smart contract on 120, then that should work. And on line 138, from line 138, we assert that when we call on the query entry points, the get count returns the value 5, which is the newly set count. So those are the tests, and we can run this test using blast rust test command. So now we've had a look at our smart contracts. Let's now test out the blast command. We're going to compile, test, and deploy the smart contract on our local node. So blast help, this shows us the possible commands we can use. We have the blast init, blast compile. Blast test is used to run the JavaScript tests. You would see that in the tests directory, and blast rust test is used to run the smart contract rust test. We also have the blast node that is used to interact with we can use it to start and stop the local node. And blast keys is used to manage the Cudos account. So now let's use blast to compile our smart contract. I'm going to run blast compile, and this compiles our smart contract and creates an artifacts folder in our root directory. So we have a WebAssembly file named alpha. We also have the checksum, which can be used to verify the smart contract when it's uploaded into the blockchain. So now we want to test the smart contract. Since we're running the rust tests, we're going to use the command blast rust test. Our tests have now successfully run, and the 3 tests passed. Now we want to move on to the JavaScript test. Before we can run the JavaScript test, we need to start our local node. So now we have to start the local node using blast node start command. While the local node is starting, let's have a look at our alpha.test.js file. It uses the Cudos to blast library. On line 1, we import it using the require keyword. On line 7 to 10, we create variables that are going to be passed in as messages. The blast testing uses the Jest framework. So before all the smart contracts are run, we are setting number 1 on line 15. We're going to get accounts and we're going to create accounts Alice and Boss using the blast.getSigners method. And what the getSigners method does is that it uses accounts defined in the local accounts.json file to populate or create accounts. So we're creating the account Alice and Bob. We're loading the account on line 16 using the blast get contract factory command, passing in the contract alpha. So that tells it to load the contract named alpha in the artifact. And we're going to call contract.deploy. What contract.deploy does is that it deploys the contract and also initializes the contract. So our first test on line 20 is to test if the count increment works. So we call on contract.execute, passing in the message increment, which is the type of message that increments the smart contract. We're also passing the sender info.sender as Alice. Now we query the contract on line 22 and we check if the result equals 14. On line 26, we test if the contract can be reset by the owner. Remember that we initialized the contract with the owner set as Bob. So now, calling on the contract.execute method, passing in the message reset, and the signer as Bob, we call on the execute method. And to confirm if this was successful, we call on the contract.query method, and if the count has been reset to 1. And lastly, we are testing if the contract.execute rejects when we pass in the reset message and the signer as Alice. So we assert that it rejects and throws an unauthorized error. Now we're going to run blast test to run this test script. Our tests have successfully run and all of the tests passed. Now let's have a look on how we deploy the smart contract. We have a script folder in our root, and this script folder is how we can interact with our smart contract using Cudos Blast. We can also create our own scripts and run them. So in the deploy.js, inside deploy.js, you see that we are creating signers the same way we created signers in our test. We're also loading the contract using getContractFactory. On line 7, we create a constant variable containing our initialization message. Line 8 is very important as this is how we deploy the smart contract. This is very similar to the method we used in our test. Remember, we're using Cudos Blast, and you can also write your own script this way to interact with your smart contract. So now we have deployed our smart contract, and we can interact with the smart contract using the interact.js script. Coming into the file, we're going to paste the contract address onto line 5. You see that apart from loading the contract using the name of the contract, we can also get contract from address. And in this case, the address is the address we just deployed onto. On line 7, we have a query get count variable, which contains the query message to get count. And on line 8, we actually run the query and we call on contract.query to get the count, and we log the count on line 9. We have the message increment, which contains the execute message of variant increment. And on line 12, we call on the contract.execute function, passing in the increment message and the signer as Bob. We also log the result of that. And you can see the log contains the message index, the log. If we had events, it would be there. The height of the blockchain, the transaction hash, gas used, and gas wanted. So on line 15, we make another query to read the state of the smart contract, and we log that as well. So that is how you interact with your smart contract using the Blast library. You can read more about the different methods by checking the repository or the NPM page. That's where we're going to call it a wrap for now. Thank you for watching. Please do watch out for my next video, and that's all for now. Make sure you like, comment, and subscribe. Thank you. Bye.